For circuit 1, using the superposition theorem, we perform a mesh analysis for each subcircuit arising from the aforementioned theorem. With this, we obtain three equations used to solve for A2, A1, and AX, except for the analysis for the first current source. The same equation is generated differing in the definition of A2, the process to calculate AX, and therefore the BX corresponding to each subcircuit is the same in all cases. The BX of each subcircuit is calculated using Ohm's law, multiplying the resistance value by the corresponding A2. And in the end, all the BX primes are added together, resulting in the total BX. There is a sum. For the circuit 2, we use superposition for the circuit mesh test. Mesh analysis was done for each case of superposition with the values A1, A2, and A3. We obtain A0. A system of equation was generated from each case of superposition. The resistance where B0 is being solved depends only in A2. In the system of equation, only the value of A2 is used, and by using Ohm's law, it's used to obtain the voltage value for each contribution of V0. Finally, the contributions are added together and we obtain the value of V1 with a sum. In the circuit 3, we start by simplifying the base circuit to have the simplest way of this, and we ignore all the voltage sources since we assume that they will be off, and to calculate the Thevenin equivalent resistance. In this way, we use the delta star method to calculate the value equivalent to the set of resistances in the circuit. Returning to the simplified circuit, we perform mesh analysis in the two meshes that we obtain and we have left in the circuit in order to obtain a pertinent system of equation. Based on Ohm's law, we delimited what will be equal to the value of the mesh currents, assuming that there is a ground connected. We substitute the values of A1 and A2 in the Ohm's law calculations, and this allowed us to obtain the values of the voltages at nodes A and B. By making the potential difference between nodes A and B, we were able to make the Thevenin diagram and later the Norton diagram. And for the circuit 4, the first thing that we do is calculate C1 with the capacitance formula, and then we simplify the capacitances what are in series to a single one with the formula of capacitance. Then we simplify the capacitance that are in parallel with the formula to make just one in series with the rest of the circuit, and then we calculate the equivalent resistance of the circuit closed by the capacitor. Then we calculate the time constant with the formula. After we calculate the current with the data obtained, and finally we calculate the energy storage in the capacitor at time equals zero with the formula too.